Hi guys. So today, I'm Ryan and my friend Daniel here. We will both be talking about a practical introduction to substructural type systems. And we'll be doing it through the lens of two different systems. One is a very new extension to GHC that's being proposed called Linear Haskell, and another one called Rust. Well, another language called Rust. That's not a GHC extension. So, not that I know of. So today we're going to go through a kind of a motivating example, and that's going to actually thread through what we talk about. Then we're going to talk a little bit about substructural typing. We're not going to go too far in depth, just a kind of brief introduction. We're going to go a little bit over linear Haskell, and then we're going to hopefully see that we can do our resource management in a better way. We'll see if that's true. And then we'll talk a little bit about how Rust can do similar properties. And then we'll finally end with substructural types in medical imaging. So you probably didn't expect to hear about medical imaging today, but my colleague and I are both in medical imaging. So we hope to eventually use something similar to these ideas in our work, or we just waste our company's time by being here. So what can substructural types do for us? So they allow us to do a few different things, and there's different ways that these guarantees can happen. But they basically, as kind of an overview, what we'll be dealing with here today is guaranteed uses of values. So you could say, for example, you can guarantee that a list was consumed completely or permuted by any function. We want to be able to show that we can have safe guarantees for channel communication and also safe handling of resources. So the one we're going to thread throughout this entire presentation is the safe handling of file resources. So say we have the following API for accessing a file. So this is most of the talk, or most of my sections in Haskell, but ish syntax. But say we have a file. File is a file handle, and then a file path is just a string. So that's the location of which we actually open the file. We can open and close files using the standard I/O functions that we have for opening and closing files. And say we can also have a function that's append to a file. So it just takes a file and some bit of string that you have and puts it at the end. And we also have, the only other function we have is now, which gives us the current time. So say we want to build a function that basically uses all of these to take an existing file and append the current time. It could say be your really lazy way of figuring out every time you ran a program, was it would just log the time that you actually ran the program to a file. So if we were to write this out, you'd probably, like in Haskell syntax, if you're just using do notation, it'd be pretty simple. You first open the file, get the current time, append the current time to the file, and then you would close it. So hopefully everyone's done this before. It's not super complicated. But one thing that I've definitely done is that you can make a mistake. So this is a more obvious mistake where you close the file before you append to it. And unfortunately, the Haskell compiler and most other languages will let you do this. So in this example, it's particularly clear, but you might have a bunch of intermediate functions in there that call out or move the file handle around. You don't exactly know, it might accidentally not get closed when you expect it to. So the problem we have here is that the developer was responsible for a property that the compiler should ideally be checking for us. We have to go check that if you've opened a file, you have actually closed it, right? There's nothing currently in the compiler that tells you, or in the type checker for most languages, including Haskell, that will tell you that you actually did this correctly. It will throw you an error at runtime instead. So what's the kind of basic problem? If we look at the API for this kind of interface, what we see is that once we've opened a file, we can kind of do a lot with this file handle, right? We can pass it to the append function, we can pass it to close, we can drop it, we can make duplicates of it, we can do all sorts of things with it. It's really unrestricted in the way in which we use it. And so what we'd like to be able to, so you can have it be threaded in an incorrect way. What we'd like to eventually do is, and show, is that we have a way in which to basically sequence all of these operations together, and there could be branches in there, but sequence all these operations together such that they always start and end with an open and close. Such that you can never have a case where you've opened it and you've left it, or you tried to close something that wasn't opened in the first place. So what we're kind of try to go to towards the end is something that looks like this. So this is not actually in linear Haskell syntax, but you would open the file, get the current time, and then you would append to the file handle and get a new file handle. It's to the same file in this case, so it's not terribly interesting. Ideally, it doesn't point to a completely different file. That'd be a problem. And then you close it. So here, F is used, it's created and then used once in the append, and then F1 is created and used once in close. So this helps us kind of thread through things. So to get to this kind of way in which we can thread through and have the compiler force us to thread through the file handle or a resource. We're going to look at a little bit of linear typing and substructural types. So I guess how many people are familiar with what substructural types are? Okay, so a handful. So in which case, this part will be boring. But so basically, the substructural type systems are based on the property of, so most type systems have three properties that kind of emerge out of their judgments. So these three properties are exchange, contraction, and weakening. And substructural type systems are about dropping one or more of these, or not necessarily dropping them, but potentially weakening them, or having weaker forms of them. So I'll go through exactly what these three different substructural rules are. The first one is exchange. So the exchange rule basically allows us to type check in any desired order when multiple terms are basically in scope for our type checker. So for example, if we have this function called exchange, and it brings two things into scope, x and y, when we actually go and try to type check our program, you can use the proof of x or the proof of y in any order that you choose. And they can kind of be moved around nice and easily. It doesn't really matter. If you restrict this property, if your system does not enable exchange, what it means is that you have to use all the terms that have been introduced in the stack order that they've been introduced. So for the exchange example, you would have to type check y. You would have to be able to prove that y has that correct type and use it before you could actually go ahead and use the proof of x in your type checker. So that's exchange. Then there's contraction, which allows us to make duplicates of type statements and type proofs. So it allows you to use a variable twice. So for example, in this case, we have a duplicate function. And what it does is it just takes a object and makes two copies of it, right? So in this case, when we're trying to type check it, we'll use the proof of proof that x is a, both on the left side and the right side, right? The fact that we can do that is pretty nice in most programming languages. If you restrict this property, that means you can't use a term more than once. Once you've actually type checked that something has x of type A, you lose that proof. You can no longer use it, which means you can't use it anywhere else when you're trying to use your type checker. You could prove the left side has type A or the right side has type A, but after that you couldn't prove anything more. And then weakening, the third rule, means that we can discard unnecessary type proofs. So example for here, the example would be the kill function. So for kill, we can take in a variable and just return unit. So when we're type checking the value of unit, we don't actually need to know that x is type A. It's a little bit irrelevant. And so we can drop it when we're actually doing the proof. If we restrict this property, it means that we have to use a term at least once. Basically, weakening, since it allows us, the property allows us to discard any unused proofs. If we are not allowed to use weakening, this means we can't discard any proofs. We have to use them. So substructural types, there's a few different basically ways that you can add or drop different substructural rules or structural rules in order to get a different type system. And there are 5 ones that are pretty common. It's technically the whole field. You could discard any 1 or 2 of them, but only certain ones have found to be particularly useful at this current moment. So the most common one is unrestricted. So this would be Haskell and whatever your other favorite language is. So this allows you to use a variable somewhat willy-nilly, which is really nice. You can make copies. You can use it twice, use it 0 times. It's standard programming affair. The next is relevant type systems. So relevant type systems are where we drop the weakening rule, and then this leads to an interesting case where we can't not use a variable. We can use it more than once, but we can't not use it. We have to use it once or more. Then there's the slightly more popular affine type system. So affine type systems are where a variable, you drop contraction. So contraction was where you could use something more than once. So in this case, since we only have exchange and weakening, what it means is that we have to use a variable 0 or 1 time. So this is the type system that you would find in ALMS, which is a programming language by Jesse Tov, and Rust has an affine type system. And then linear is kind of below both of these two. It has neither contraction nor weakening. Or I should say that most linear systems have very controlled contraction and weakening, such that it means you have to use every variable exactly once. You can't use it more than once. You can't use it less than once. You have to use it. And there's a fourth one, which was related to dropping exchange. So this is where you have, you can no longer exchange your type proofs when you're doing your type checking. And this corresponds to basically stack state machines, or stack machines, where you would, once you have a variable introduced, you have to use that one before you can go ahead and use the other variables. So that would be good for modeling stacks. So this is the whole overall diagram. There's more in one of Benjamin Pierce's books on advanced types in programming languages, if you're interested, which is where this diagram originally comes from. So with that, we're going to focus mostly on linear, in this case, linear and affine type systems. And so we're first going to walk through Haskell linear types, because it's a new extension, and why not? It seems fun, right? So what does it mean if we have a function that uses every element exactly once? So as a kind of overview example, we're going to use the sum function. So the sum function, I want to take every element in my list, and I want to add them all together, right? So for the sum, you'll see that this has this. The sum is takes a list of ints and returns an int with this funny little arrow in between. So this little arrow is called Lollypop. And a lot of, so I don't think it's as tasty. I don't recommend eating the screen, but it basically says that if your output is consumed once, then your input is consumed once. And so that enables a guarantee on linearity. So here we are linear. Anytime you see a subscript L in any of these slides, it means that it's just the linear version of a function.
I've never been in touch with linear type systems before, but when you say my output is compute, or how my input need to be consumed, could you say it's an implicit proof of total?
It's an implicit proof.
It's a function of total because.
Yeah. So in practice, so the way that this is offered, basically, whenever you have a partial function, and then you have that wildcard statement that would lead to error, that is actually accepted by the type checker, and it basically can't determine what happens in that case. It can't determine how the variables are going to be used. So at that point, it doesn't give you totality. In the case of partial functions, it will still throw a runtime error, because basically it doesn't know what that last rule should have been, or last set of rules. Yeah.
What does it mean to consume a list exactly once?
So we'll talk about that in the next slide, or in the next few slides. So any other questions? Okay. So yeah, this is the probably pretty standard sum function that you've seen. So what happens if we, I should say that this presentation is a literate Haskell file, so you can download and run it yourself. And you can run the linear extension, and everything should type check in this presentation. So, oh, it's way at the beginning. If you go to GitHub/Ryan Orendorff, it should be one of the repos there. So here we've tried to use x twice when we've summed the list. And so clearly we've used the head of the list more than once. We can visually see that there's a problem. And when we actually run this through the linear Haskell type checker, it does tell us this. It tells us that, unfortunately, the weight, so the weight is the number of times that you've used a variable, the weight of x is actually omega. So there's a semi-ring around kind of weights, but 1 plus 1 is infinite, basically, in this algebra. So it doesn't really, it doesn't tell you 2, it tells you infinite. So it just tells you it's been used more than once. And similarly, if I decide to, in this case, this would be the length of the list, I guess. But if we decide to instead drop using x, then we get a similar problem. And the type checker will instead tell us that we forgot to use x, right? That it instead has weight 0. So we violated linearity and we forgot to use it. So what does it mean to consume a variable, right? So to consume a variable, it's either an atomic, there's a few case rules. It can be an atomic base type like int and bool, or something else. That you just evaluate once. For a function, you pass it one argument and consume its result exactly once. So we're going to get into functions a few times in the next few slides, because there's a little bit of a trickiness here. And what it is that, say we have a linear function f that goes from a to b. Then if f of x is consumed once, the output is consumed once, then the input is consumed once. That's all the function guarantees. It doesn't guarantee that this is linearity on the arrow, not linearity on values. So if you consume that output 5 times, that also says that you can guarantee that you've consumed that input 5 times. So it's not that the value is used linearly, it's that this relation is held. Hopefully we'll see a little bit more of that. And then for any algebraic data type, you pattern match and consume all of its components exactly once. So this is the recursive case, right? So for a pair, it means you would pattern match on that pair and consume each component exactly once. So,
Sorry, quick question.
yes.
Can you go back? So with a function, what if your argument is itself a function? Would you have to consume every input in the domain before that function is considered consumed, or is it if you evaluate that function once, it's considered consumed?
So if your input to that was is a function instead of a, like a was a function.
Yeah.
So you would have to say that guarantee would say that you would use that function once. Not that, but that makes no guarantees on what that function actually does that you passed in. It just says that you use that function once. It can use its input a billion times if it so chose. So there's a few gotchas, and this will come up with the function arrow a few times, but the linear arrow says exactly how it uses its argument. It does not restrict what's passed to it. So again, this is where we're talking about linearity specifically on the arrow. So say, for example, we take a function f, which is linear, and a function g, which is nonlinear but uses f. So here it might be convenient or desirable to think, oh, linear functions allow us to basically use variables that have only been used once. But if they're inside a context that's nonlinear, then we can't make that guarantee. That input that's been passed to it, while the f will use it once, it doesn't guarantee that the larger scope that it's in will only use it once. So if x was a pointer, we couldn't guarantee that f got a unique pointer in this particular case. You can do that by threading together a bunch of linear functions and basically guaranteeing that whenever you have a pointer, you pass it off to this next partner in the chain of command and the compositional chain. But once you have the nonlinear arrow, you don't exactly know what's going on with the input. Although f is still guaranteed to use its input exactly once. And you might be wondering how do data types work. So in data types in linear Haskell are actually all have linear arrows inside of them instead of regular arrows. So this might be like, oh, well, I don't want to use all of my data types in Haskell only once. That would seem to be a pretty big restriction. But again, since we're using it in a nonlinear context, if we use a nonlinear arrow, we can use the linear data type in a nonlinear case. So this allows us to define the first projection function. And actually allows basically, what's really awesome about this extension is that it allows basically all the Haskell code that exists to currently exist as it currently does. There's no modifications that are required because they all use this unlimited arrow, and everything becomes, you have no linearity guarantees, and they're not enforced at that point. So when they enable this extension, you could add linearity to parts of your program that you want to specifically guarantee some linear component, but everything else that you've ever written should ideally work without any problems. Now note, if we try to do a linear first, this doesn't work. So we get the linear sad face function, which I think that should be a compile check. If you have a sad face in there, that should totally tank your program. But basically, if we try to take the pair A to B and we try to linearly take out just one component, we'll get an error. Because this means that we didn't actually use our B correctly. We used it with weight 0. So this is great. What it means that is the linear data types that are defined inside linear Haskell work in nonlinear contexts. We don't need any special data constructors for linear versus nonlinear data. You just use the standard data constructors or type and data constructors you're always used to. There are certain cases where you would want to basically promote a linear value to be used in a nonlinear context, or a little piece of data. So for that, you can define, and this is not anything special, you can just write it out normally. It's not defined in linear Haskell itself, but you can basically produce a value of unrestricted A, where it takes a type A and then returns to you an unrestricted A. And then notice here you have this regular arrow again. Instead of the standard, this uses GADT syntax, but you have the regular arrow here. So once you've done this, you've said, okay, I'm throwing away my linearity guarantees in some regard, because now I'm using things in a nonlinear context. So this does allow you to define the projection function that you might desire to get one particular part of a pair out, but you have to specify that one of the parts would be unrestricted to do so. So hopefully we can use all those ideas that we just came up with to come up with a better way in which to do the file handling case. So let's say we have the following API. It's the same API that we had before mostly. So we have file, which is a file handle, and file path, which is just its location. And we can open and close a file. So here, note that opening a file consumes, we don't really care what the string was. We don't need to consume that linearly. But now we have this IO of L. So now we're dealing with a linear IO monad, and it gives us back a file. And then close linearly takes a file and returns a IOL of an unrestricted unit. So the reason why it's unrestricted is that's actually to work with the linear base package that they have produced to go along with the linear Haskell, but basically allows us to eventually run linear I/O monad computations inside I/O. We can also append to a file. So for appending to a file, we take in a file linearly and some piece of text that we want to actually append, and then we produce another file handle in this case. So note here that text is also not unrestricted. So we don't actually, we make guarantees on the file handle. We're not making guarantees on to exactly how you're doing the append. You could potentially append the same string a bunch of times, or you could disregard your input string, whatever. And then here, this is just a regular I/O, the same now function. So now, when we put this all together, you've seen that linear I/O monad. We need to define what that means. As you would probably guess, the nature of the game is replace all the arrows with the lollipop. So return becomes the same one, except for now you return using the linear arrow. And bind is basically the same type signature, except for now you use linear arrows in the bind. And basically the fact that, so normally bind is written as its input value in a continuation k, the k being the second part of the type signature. That continuation forces you to thread through that whatever value you produce in a linear fashion. It emulates a linear value in a sense, but it forces us to use that value linearly instead of relying on the function arrow for linearity. So now let's take a crack at that example again. So we had append time to file. So for this case, first we're going to get now, just get the current time, only because we are going to otherwise run everything in the linear monad. And then we're going to bind that to, we're going to do this run L, which runs our linear I/O monad, and then we're going to do the same file procedure we were doing before. We're going to open, append, and close. And note here that, so this does type check, but note here that the file handle is threaded through, and you don't have to, you can overshadow and use the same name, but in which case, to make it a little clearer, I've said that F1 is the output, and you can see that each piece is used only once, each file handle. So now, if you have the sad version of this one, you would potentially say try to open and append to the file, but you forgot to close it. Right? You didn't actually handle your resource properly, and now it's just left dangling, and hopefully the computer will, on termination of the program, will actually clean this up for you. If you run this through the type checker, it will tell you that F1 has weight 0. So you've produced a file handle, but you forgot to use it. So here we've shown kind of an example through linear Haskell that we can actually take our prior file access and turn it into a safer version, where whenever we open a file, we can guarantee that you have to have closed it. No matter how complicated this I/O component gets, assuming you've designed your interface correctly, you can guarantee that once that resource has been opened, it will be closed.
Question.
Yes.
What would happen if you forgot to bind F1 if you just left that off on that line?
Bind F1. Then it would also just tell you that you had weight 0.
So if,
that you forgot to use it.
if I just typed append F on that line, the compiler would, what would the compiler
I think it would,
would make up a variable name?
it should tell you the same thing, that basically you've used it 0 times. Because you just haven't given it a name in this case.
Wow, awesome.
Yes.
How does this respond if you have an exception during the file operation?
Yeah, so that is a great question. So this example does not currently handle exceptions in a graceful way, but the linear base library that the Tweed guys have built around linear Haskell has a resource-safe linear I/O monad that basically guarantees that anytime you have an exception, it has a resource map, which is a list of integers, which maps a list of integers or any integer to some resource. And then on exception, it actually forces all closes. So there is a way to, in this case, they actually, if you look at the code behind this, it does use the resource management I/O that they have built. I've just slightly changed the syntax a little bit. But yeah, so you can do that on exception if you build it correctly. Are there any more questions? Because actually we're going to be heading out to Rust land. Yes?
If you were not using this resource package, you could still run into the problem that an exception prevents your file from being closed. And you have to wait for the PC to eventually do it.
Yeah, So the resource management IO part should tell you, it should eventually clean it up.
But this example doesn't use it. So if I would write it down in your Haskell right now, I would only be safe for non-exceptional workflow right now.
So actually this one does use it. So if we look in,
I don't want to look for talking.
yeah, so here is that function. But basically this SIR component, this is the system IO resource one, that particular IO monad does enforce this. So you can use that from the base library that they have provided. So they have two ones in their base library. They have a linear monad and a resource safe linear monad.
But if I would use only the linear monad, I would be subjected to exception analysis.
Yeah, potentially. So yeah, I guess this helps in some regards, but it can't help you shoot yourself from shooting yourself off in all cases. Yeah, basically. We're not quite. Yeah, the compiler is not quite that perfect yet. Although then, if it's that good, maybe we're out of a job because the compilers will just do everything for us. Okay, if there are no more questions, I will pass it off to.
That's the linear bind, right?
So that's the regular bind.
Okay, it's the regular bind, okay.
Yeah, that's the regular bind. The linear bind has the L at the end. It's used implicitly inside. So I used an L at the end, the do L. Sorry if that was a little confusing, but yeah, the do L just represents all the binds that are inside that do block are the linear bind.
Alrighty, so we're going to move on to Rust now. And so I guess one of the interesting things about Rust, and obviously relevant to this talk, is it's a mainstream language, so to speak, that ships with a substructural type system baked into the language. So let's just move into some code example straight away. And if you're not familiar with Rust syntax, don't worry about that too much. It's not really what we're emphasizing here, but this is a using a file in Rust type of example, similar to what Ryan showed in the linear Haskell. So this is a very imperative code here, but we're opening up a file, reading it to a string, appending it, and then we're going to close the file here with this drop f here, okay? And so this will work. This is, fine and dandy, but what if we forgot to close the file? So we didn't call this drop. What's going to happen? So to answer this question, we have to talk about the ownership type system in Rust. So the Rust compiler establishes and tracks ownership of all resources in the program. And so one thing that then allows the compiler to do is automatically insert calls to drop when an own type with move semantics goes out of scope. And so one of the big things that this provides in Rust, it uses it for, is it provides automatic memory management without a garbage collector. And that's a really useful thing. But it also means that you cannot forget to finalize these resources. So for example, the files or sockets. And you also can't forget to free a data lock, for example. So if we go back to this code, in fact, the compiler will manually insert that drop that we forgot. So this is actually fine. And this is actually how you would write it in Rust. You don't typically manually insert drops. But what if we, try to close the file early? So you can see here now the drop. We open the file, but then close it, and then try to read from it. So what's going to happen? Well, the Rust compiler is going to say, nope. As you can see, it says, hey, it says you moved, but you used f here, and it's called a drop. And then you tried to use it again after that. And that's not okay. You can only use a resource once. And just to show it's not special about drop, this is true also if we package the file off and send it to another function. We're also going to get this compiler error where Rust is saying, hey, you've tried to use this resource twice and you can't do that. But just to connect back to what Ryan was talking about, you can do sort of this linear threading or threading of the file through. So if we have some process function that takes a file and does some stuff and then returns the file handle. So we can use that in this way. So you can see here we have, we send the f off to process, but it sends it back. It moves it back, and we bind that to f moved back in this case. And then we can continue on reading from the file and so on. So I want to talk a little bit about just the nature of the substructural type system in Rust and how it kind of compares to linear Haskell, for example. So they both systems support both restricted types as well as unrestricted types, and in Rust's case, as Ryan already mentioned, they're actually affine types. And so linear Haskell, as Ryan mentioned, provides this very flexible opt-in linearity, so on the function arrow. So you can have sort of regular Haskell code, and then only in a few places as appropriate you introduce the linear arrow and you get these properties. Rust is a bit different in a few ways. So first of all, it's more of a pervasive ownership model. You don't opt into it in that sense. As you might imagine, that's important for those guarantees around the memory safety and all of that. It's also, affineness on the value, not through sort of the arrow as linear, as in linear Haskell. And so to understand about the Rust substructural type system and why it's sort of made the way it is, these ownership systems, it's helpful to keep in mind the goals of the language, or some of the goals of the language. It is a general purpose language, of course, but it really seeks to enable low-level systems programming and that automatic memory management without a GC. So that's really why it has to be this pervasive, baked-in thing that you can't really opt out of. And just to mention that this ownership system, it's important for this GC, or removing the need for a GC, but it also does really nice things like ensures statically that there aren't certain types of data races, gives you this thread safety and so on that's described as fearless concurrency. So that's really nice. In terms of the specific flavor of what this looks like in Rust, as far as the own types go, unrestricted types obey what are called copy semantics, and we're going to take a look at this in a second. And all of the other types, non-copy types that are affine, obey move semantics. And so move types are moved on use and associated typically with heap allocated data or just data you want to be affine. Copy types, on the other hand, are bit copied on use. So when you have a value and you use it when it's copy type, you can still use the original value as many times as you want. Copy type data is typically associated with primitive and stack allocated data. And custom types in the language are moved by default, affine by default, so you must opt into the unrestricted type. And so we'll take a look at that. So this kind of struct affine int situation you see in the first line, this is Rust's idiom for the new type. And so we're just having a new type around the 32-bit integer here. And so this is a custom type, and by default I said things are affine. So if we have this function take, which just grabs the argument you send to it and just drops it, if we create a value n of this affine int type, and then we call take, and then we just try to use it again by, in this case, just simply trying to print the number, Rust is going to say, hey, you can't do that. Because it's going to look and see, all right, you moved the value, you used it in this take call, and then you tried to use it again. So this is similar to what we've already seen. But one thing you'll see about the compiler errors that makes them a little more sense now, and it tells you in particular, this affine int type does not implement the copy trait. And so traits are like type classes in Haskell. So, but if we do want an unrestricted type, we can opt into it by just implementing this copy trait. And we can have the compiler automatically derive it for us. This is what you see here with this derived copy. And so again, we have this new type around i32s. We're calling it unrestricted int, and it's copy type. So now we can create a value, we can pass it to take, and then we can try to use it again, and this is fine. And what happens is when we pass it to take, is the data is bit copied and then sent to take. So it's not moved. So just to summarize kind of what we've been talking about so far with the Rust owned types, we have these unrestricted types, and that's all owned types with copy semantics. And there's also a few primitives, reference counting primitives, arc and rec, which allow for shared ownership, and so they're unrestricted as well. And then you have the other class of affine types, and these are the owned types with move semantics. And just for completion, I want to mention borrow types. So as a low-level systems language, Rust does provide a pass-by-reference types that are termed borrow types, and this is actually perhaps one of the things Rust is most known for, kind of exotic comparatively. And I'm not going to go to any detail of this, but I just want to mention that borrow types are part of the whole ownership type system, and they enforce these invariants we've been talking about. And so one of the things the compiler does with the borrow types and the lifetimes associated with them is it ensures that aliasing and mutability are always mutually excluded in the life of the program. But also of interest is borrow types themselves also have unrestricted and affine variants. And so sort of the whole story behind Rust substructural types looks a bit like this. Again, you have this split between the unrestricted and the affine types, but you have these own types as well as the borrow types, each with an unrestricted and affine variant. All right, so that's it with the Rust section, and in the last section, Ryan and I are going to talk about a little bit of some examples of where substructural typing can actually be particularly helpful, perhaps, and a lot of these are going to relate to the medical imaging work that we both do. So, here we're at a functional programming conference, so compile time guarantees are always very attractive, but I think that's especially true for us. So we write software that interfaces with these really big, powerful, and scary scanning machines. A lot of power and currents in the coils and such, and so we really need to be careful when we're controlling this dangerous hardware with our software. There's a lot of critical communication layers. We need to monitor and respond appropriately to sensors from the hardware, etc. And of course, at the highest level, we really must ensure patient safety and hardware integrity over the long term. So, we believe that a lot of our safety critical aspects of our systems could really benefit from substructural typing, as well as more FP in general. And so we're briefly going to discuss a couple things here. So the first one, I'm going to talk about session types, which I think are really interesting. And they require linear threading. So there's a linearity associated with session types in terms of their implementation. And then Ryan will finish off describing how to encode our scanner as a linear resource. So session types, I guess you can think of as extending the notions of types a little bit from describing just data to describing protocols. And so there's quite a few papers on session types that you can take a look at. But basically, they formalize the sequencing and ordering of a protocol in the type system. And so this is often discussed in the canonical example of channel-based communication. But again, the major idea here is converting a developer responsibility to a compiler responsibility, which is really nice. And because it's done through the type system, there's little or no runtime cost associated. And so basically, you can implement. What do you need to implement session types? You need kind of an expressive type system, so with data types and something like type classes or traits. And you need the linear threading, and I'm going to describe a little bit this in a minute. But there was a 2008 paper on Haskell session types, and I guess this was before the linear Haskell came out that Ryan described. And so they actually ended up using index monads instead of substructural types to do the linear threading they needed. But presumably, maybe if they were doing it again today, they would use linear Haskell. Also, recently, there has been a session type implementation for Rust, so these are quite interesting if you're interested to take a look. And so here's some of the syntax from the 2008 Haskell paper. I really don't want to focus too much on the syntax, except for the ideas, actually. And so you want to define these protocols in a type system, so you need some sort of building blocks. So you have things like the first two components they mean send A, like in the channel sense, send A, then continue with R. And there's kind of a dual to that, receive A, and then continue with R. Yep.
Are those actually meant in the sense of Gerard's of course and why not?
So unfortunately, I'm not familiar with Gerard's of course and why not.
Linear logic.
Yeah.
That's what you're typing.
I think it's like related.
Okay.
But it's not explicitly described in the paper. But yeah, there are cases where you have like the upside down version.
Oh, rad. Okay, yes, this is totally sounding like that notation. Cool.
Yeah. Yeah, and so then you have things like choose R or S, and sort of the dual to that, offer R or S. And of course, you can have a data type that just represents depletion of the protocol. So the point is like this is a very simple protocol in the type system here, right? Basically, and this is in particular thinking of communicating channels. So you have one channel that has a type of send int, receive a bool, and then terminate. And you have its partner receive an int, send a bool, and then terminate. And so the session types allow you to, at compile time, verify that these two communicating channels are compatible, and that they're protocol safe. So that's really nice. But I want to get to the linearity thing, right? So I said that these are related to linearity. How is that? So these are kind of like Haskellish syntax here, but the main point here is, let's say we have these channels that we're describing with this protocol in the type system. And we have a function. So you can make a function that takes two arguments, both of which implement the same protocol. In this case, just send an int and then terminate, okay? But in a completely unrestricted language, there's nothing from keeping you doing the last line. So let's say that this function sends an int down both of the channels it receives, okay? But if we actually send the same channel to both arguments of the function, which we can do in an unrestricted language, what's going to happen is two ints will be, in this case, will be sent down the same channel. And that, of course, violates our protocol. So it's really important that there's sort of a linear threading to session types. So in linear Haskell, for example, you could fix this by introducing the Lollypop, in this case, to the code above, and the compiler will complain and say, hey, you violated the weighting here. So session types, I think, are kind of interesting and something that maybe we can use, again, with these really important interfaces between software and hardware to really, if we can have compile time guarantees around that, that's really great. So, Ryan, you want to finish up?
Think about playing. I guess we're playing musical chairs. So, I want to talk a little bit also about an example using our scanner. So our scanner, we do something called magnetic particle imaging. It's a new medical imaging modality that is not based on, although it has a similar name to MRI, it's not actually related to MRI in any fashion. But we're trying to basically commercialize it and turn it into something from a preclinical imaging system into a clinical imaging system that we can use on patients to be able to detect cancers, to be able to detect strokes and other bleeding problems, heart problems. Hopefully it catches a lot of different diseases that we can try to see. So on the left is it's like a 900 kilogram scanner. This is pretty heavy. And does anyone know what the picture on the right is, actually? I'll give you a hint. The top bit is a little bit of a nose. And there's it's a rat. So this is the back of the head. And this is the jawline. And this is all the vasculature inside the rat that shows up when we take our scanner. So this is a 3D image that is taken with our scanner, the one that was particularly at Berkeley. Now, what I'd like to note is that we were very unsafe at Berkeley because we were not really good functional programmers at the time. But even if as we go towards clinical markets, we have to get FDA and CE approval and all these other kinds of things. And they're nice, but they're actually not as strong as the seal of approval that I want. And I want the John seal of approval. So I think we should send all scanners with the John seal of approval because it will be stronger than the FDA seal of approval. So what we would like to be able to do is to have users control this machine without destroying anyone or destroying any equipment. That's very helpful. So we'll define another API as we had done before. So we'll have a scanner with some state, and the state is currently either setup or scanning. So this uses the data kinds extension. And we have a list of and we have some parameters we can send to the scanner. This is voltages, current waveforms, you name it, FPGA commands, whatever. So for our API, we have a few things. We can basically create a scanner. I mean, obviously, it's not easy to just magically create one, but in our API, you can easily create one. You can create a scanner, and it gives you one in the linear monad. It tells you have a scanner that's in the setup mode. And then we can set some parameters on it, and note here that we take a scanner linearly and the list of parameters linearly and return a new scanner handle. So ideally, after we've run this function, the new scanner handle will reflect the new state of the scanner that we're in. Say there's like 400 volts on the coils or something like that. We use about 30 kilowatts of power, so we use a lot of current and actually not that much voltage. But so what we'd like to do is actually start it from setup to scanning, right? So we have this function that's called verify and start that goes from our scanner setup into a scanning mode. And then some get data, which just starts, now that the scanner is scanning, it actually gets the data and returns the scanner is still scanning, and an unrestricted list of floats in this case, which is actually kind of our data type. It's just an ongoing list of float 64s. And then a scanner off. So this is for any of the states that we happen to potentially be in, we can turn off the scanner. And actually I have a little bit more time than I thought, so I'm going to skip way past the end. So say we have this user-defined scan, right? Takes in a list of parameters, and inside the linear I/O, so this with linear I/O is actually using non-resource management I/O in reference to your question from before, because it was easier for me to type initially. But here, inside do-L, everything is linearly used. So we set up a scanner, we set the parameters, we verify and start, we get some data, we turn it off, and we return unrestricted in this case. But if you actually try to, say, for example, write a case where you would set up the scanner and set some parameters on the scanner, and then start it actually running and try to change those parameters at runtime, you have used SP more than once. And when you run this through the linearity checker, it will tell you that you've used SP more than once, and that therefore you cannot do this. So here we could potentially, what's powerful about this is not necessarily that we are programming these systems, but we could potentially provide guarantees to other people who would want to do different types of sequences on our scanner. It's still a research system, so there's definitely different ways in which people can operate the machine. So we want to be able to give them ways to do this that's completely safe. So, so for the possible applications for us, for all these linearity checks and the Affine type systems, is that we can do things like encoding proper hardware boot up sequences and shut down sequences with session types. And also we can do communication protocols between our real-time system, which actually sends out currents and voltages to the actual hardware, and guarantee that communication protocol is safe. And we can also say that users can define their own ways of operating on this interface that is also safe, that always leads to a close and always actually handles shutting down the scanner properly and protecting the equipment and the patients. So in this case, the patients are rats at the moment, but ideally people eventually. I mean, if you want, you guys can be like the first testers, but it's still a little experimental. So in conclusion, the substructural types allow us to, again, correctly reason about make correct, stronger guarantees about correct resource usage, correct interface between two systems, and potentially has medical applications. We're hoping that we'll try something like this at our company. So thank you for listening, and if you have any questions, let me know.
You mentioned that, or it was mentioned that in linear Haskell, the linearity is sort of built into the function arrow, like the Lollypop operator, but in Rust, it's like, I guess it's practical values instead, or? Yeah. Can you comment on, like, are these, like, equivalent, or is one more expressive than the other?
So the way in which this, so the Tweak paper, the guys who introduced the linear Haskell extension have a great talk about this. But basically, for one, they like the linear arrow because it matched closer to the linear logic notation. And two, it allowed them to basically interface nicely. It seemed like it was harder with linearity on the value, which was basically a kind level property that they were handling. They were setting the universe into different sets of types. They said that was harder to interface with dependent types. So there was a question for a while as to whether or not dependent types and linearity could work together, because the problem with like linearity is that once you've used a proof, it kind of goes away, and then if you're depending on it, there's a question of whether or not you can still use it. But Connor Mcbride actually published an interesting paper called I Got Plenty of Nothing, where he uses this concept of nothing, of zero, but to be able to basically show that if you use this linearity on the function arrow, then you could potentially later in the future also combine it with dependent types. So I think that's why they wanted to do that. Also, you can like kind of emulate the linearity on the value by basically dealing with everything in continuation form, or the double negation trick.
Back in the days, the clean language had uniqueness typing, which is more or less equivalent to linear typing, but slightly different.
Mm-hmm.
Can you comment on why we should use one or the other, and why you chose one or the other?
Yeah, so that's a great question. So there's a few languages besides clean that also use, they just has uniqueness types. There are just certain cases where, depending on exactly what uniqueness types are really helpful for a lot of resource management, whereas the linear arrow thing is really helpful in functional programming for deciding when things can be fused. So it's really good for program compilation and other things. So actually they showed this, if you get a chance to read the Tweak paper, which I highly, highly, highly recommend, they show an example where they basically deal with serialized data, but they don't actually unpack it. They leave it in the serialized form, and they're able to get actually quite a bit of performance out of the system, because Haskell does have a cardinality checker in it. It allows them to kind of fuse a lot of things that would otherwise not necessarily fuse when they're doing the program compilation, and that allows them to reduce potentially allocations and numbers of steps and that kind of thing. Yeah. Any more questions? I guess I'm out of stuff, so.